Now we're going to look at transformations of graphs today, and we're going to do a quick little review of some of the translations and transformations that you saw from Algebra 2. So the first one starts off with vertical translations. That means it's going to move up and down, and that occurs when we take a function and we add or subtract something at the end. Horizontal translations, that's going to move the graph left and right, and that happens if we have x minus a in parentheses or x plus a. The reason I put x minus a here is if it says plus, it actually moves it to the left, and if it says negative, it moves it to the right. So it's the opposite of what you might expect, so hence the negative sign to show that. If we put a number in front of a graph, then that's going to stretch the graph. So think of the graph of x squared and the graph of 2x squared, how it stretches the graph. A horizontal stretch, that's going to be something like, for our questions, sine 2x, sine 3x. And the one over here shows you it actually does the opposite of what you would expect again. So 2x actually squashes the graph. If you do a half x, it actually stretches the graph. So it does the opposite of what you might expect there. This one we should be very familiar with. Think of x squared and think of negative x squared. It's just a reflection in the x-axis. And f of negative x is going to give us a reflection in the vertical axis or the y-axis. This one's also going to be relevant for even and odd functions, which we're going to talk about in the next chapter. Now, to know transformations of graphs, we've also got to know the original graphs. So I'm just going to talk a little bit about the reciprocal graphs. So we should recognize sine x here. And when we come in to do the reciprocal graph, we're looking for a few key points. So anywhere this equals 0, when we do 1 divided by 0, that's going to be undefined. So we notice we've got asymptotes of 0, 180, and 360 for the graph of cosecant. Now, one way to remember this graph is that, and this is actually something a student told me, is that you take this part of the graph. If you flip that over, then it becomes this shape, and that's how she helped to remember this graph. And actually, it's a much better memory tool than what I used to do, which was trying to just learn the graph. So the U shape here, if we flip it over, then it becomes the N shape, and that's that graph. Notice that it goes to negative 1 and 1, and the reason for that is if we do 1 divided by 1, we get 1. If we do 1 divided by negative 1, then we end up with negative 1. Now, if we look at cosine, same thing. First of all, to figure out the graph for secant x, look to where it equals 0. 1 divided by 0 is going to be infinity, or undefined. So we know we're looking at 90 and 270 here. And the same sort of idea, we're just going to flip that graph around. I'm just going to do like a reflection here. The U-shaped graph is going to flip over. And also, high point of 1 for this, or sorry, it starts at 1, and then this point here is going to be negative 1. And then the same for this point here, flip it over, so it becomes like this. So another useful tool for remembering that graph. When we get to tan, 0, 1 divided by 0 is going to be undefined, 180, undefined, and 360. And also an extra problem for this, when we have an undefined, 1 divided by something that's undefined is going to turn out to be 0. So at 90 we actually have a value of 0, and at 270 we have a value of 0. And it looks very similar to tan. Tan's always increasing, cotangent is always decreasing. So that's quite an easy graph to remember as well. But make sure you know those 6 basic graphs, otherwise you won't be able to do any transformations at all anyway. Now the scale on these graphs might look a little strange, and that's because I had to do this in radians. So 3.14 is pi, which is why that first value is there, which we normally think of as 180. So when we're given a graph with something on the end, we've just got to think what type of transformation that is. That's going to be a vertical transformation. So if it says plus 1, what it means is every point, we're just going to add 1 to it. And if we can plot the points, then we should be able to figure out what this graph actually looks like. It's easier to do it for values that are actually integer values. So there's 0, so add on 1, and you get 1. And actually we can check that from here. If I drag this across, you can see that it does go through all those points there. You can do the same thing if it's sine x minus 2. Take key values and then subtract 2 from them. So 1, 2. Now this is at negative 1, so negative 2, negative 3, 0. This is 1, so that would be negative 1. 0, subtract 2, give me that value there. And if I join them up, you can already see that nice shape there. But let's just check how accurately I actually did that. I lost a little bit of accuracy there, but you can see what I was trying to do. Now we can also do this for negative sine x. Now I got negative sine x plus different numbers. Now when we have multiple combinations, transformations, we have to make sure we follow order of operations. So multiplication is going to come before addition for this. So if I'm going to do negative sine x plus 1, I need to do negative sine x first and then add on 1. So negative sine x is just your reflection in the x-axis. So this is going to come down here, and this is going to move up here. And we should be able to see that on this next graph. So that's what the graph of negative sine x looks like. So if I want to do negative sine x plus 1, what I'm going to do is take this graph of negative sine x and move all the points up one place. So negative 1 moves up to 1. Now 0 moves up to 1. Now I'm going to have to get rid of the graph of sine x to do this. And if I join those points up, then it should look like this. And you can see that I managed to do a pretty good job of doing that. So order of operations is important when we're doing those types of questions. Now another type of transformation is if we have a number at the start of the question. So this should change the height of all the points. So if I was to do 3 sine x, what I'm basically doing is taking sine x and then timesing the points by 3. So 1 times 3, 3. 0 times 3, 0. 0 times 3, 0. Negative 1 times negative 3, negative 3. 0 times 3, 3. And we can join them up. And you can see what actually happens is it just makes the graph steeper, or it changes the amplitude. And we can do the same thing with other graphs with negatives in front. Now the one with negative, we can do it in 2 stages. If I was doing negative 3 sine x, oops, then I could do the graph of 3 sine x, and then I could flip it because of the negative. So if I do negative 3 sine x, there should be a reflection in the x-axis, and there you go. You can see that's exactly what happened. Now we could also do the same sort of rules with cosine, so just make sure you're familiar with all these. So the number at the end means we're going to move the graph up or down the appropriate number, so this should just move the graph up one place. If we have the negative and then the plus, that should make it flip first, and then move it the appropriate number of places. So we flip the graph over and then moved it up 3 places. And the one with the number at the start of the question, that should change the height of the graph. So instead of being at 1, it's going to go up to 3. And also, and we must have skipped this on the previous one, we also got the graphs that move the horizontal translations as well. So I had to do this in radians, so pi over 2 is 90. Pi is 180, and 3 pi over 2 is 270 if I was to do this in degrees. And this is the one where you'd actually do the opposite of what you'd expect. So plus 90 doesn't mean you move it 90 degrees or pi over 2 to the right. It actually goes pi over 2 to the left. So all these points are going to move over just a little bit. So this point here is going to move across a little bit and so on. Now this one's a little more difficult to do by hand. So you can certainly see the top of the graph has been moved to the left, the bottom of the graph has been moved across, and so on. Now a couple of these graphs will actually look the same. X plus pi, I'm just going to get rid of these 2 graphs for a second. If I was to do cosine of x plus pi, it would actually look the same as cosine of x minus pi, and that's because if you do 180 one direction, that's the same as doing 180 the other direction. Now, one of the best ways of actually playing this is actually to go to the Encode Wave Rider, which is on the BBC. Now, I've got a link on my page. If you type in Wave Rider and then BBC, that should take you to this page here, and you can actually go ahead and play this game here. Now, when you come to play, I'm going to make a few recommendations. I would certainly play the rookie version, and it gives you a chance to manipulate the different values, the coefficients, so you can change the height, you can move the graph up and down, you can move it left and right. As I'm not quite sure on the copyright rules with this, I'm not actually going to play this game for you, but that's one that you should certainly try to get used to those little rules.